This video is a reading of Section 6 and 7 of Chapter 4 of Paul Hewitt's Conceptual Physics textbook. Section 4.6, Net Force. In the absence of force, objects at rest stay at rest, and objects in motion continue in motion. More specifically, in the absence of a net force, objects do not change their state of motion. For example, if you push with equal and opposite forces on opposite sides of an object at rest, it will remain at rest. The forces cancel each other out and there is no net force. The net force is zero. The combination of all forces acting on an object is called the net force. It is the net force that changes an object's state of motion. Figure 4.10 shows how forces combine to produce a net force. When you pull horizontally with a force of 10 newtons on an object resting on a frictionless surface, the net force acting on the object is 10 newtons. If a friend assists you and also pulls in the same direction with a force of 5 newtons, then the net force is the sum of these two forces, or 15 newtons. Figure 4.10 on top. The object moves as if it were pulled with a single 15 newton force. However, if your friend pulls with a force of 5 newtons in the opposite direction, then the net force is the difference of these forces. You subtract them and you get 5 newtons of net force. Figure 4.10 center. The resulting motion of the object is the same as if it were pulled with a single 5 newton force. So let's examine the figure, figure 4.10. When more than one force acts on an object, the net force is the sum of the forces. When forces act in the same direction, the net force is the sum of the forces. When forces act in opposite directions, the net force is the difference of the forces. And remember, difference means to subtract. So in this top row, we have a 5 newton and a 10 newton working together, same direction. The net force is 15. Here we have a 10 pulling right and a 5 pulling left. They're working against each other, so we subtract and we get a 5 newton net force pulling towards the right. In the bottom, when we have 5 newtons pulling left, 5 newtons pulling right, we subtract them because they're opposite. 5 minus 5 equals 0. There's 0 net force. The forces are balanced out and that object's not going to accelerate. Section 4.7, Equilibrium, when the net force equals 0. What forces act on your book while it is motionless on a table? Don't say just its weight. If only the force of gravity were acting on the book, it would be in free fall. The fact that the book is at rest is evidence that another force must be acting on it. This other force exactly balances the book's weight and produces a net force of 0. The other force is the support force of the table. Support force is often called normal force, as shown in figure 4.11. The table pushes up on the book with a force equal to the book's downward gravity weight. When an object is at rest, with the net force on it being 0, we say the object is in a state of equilibrium. The resting book is in equilibrium. Let's look at the figure 4.11. On the left side, the table pushes up on the book, that's this upward arrow, with a force equal to the downward weight of the book, which is this downward arrow. On the right, the spring pushes up on your hand with the same force you use to push down on the spring. The forces balance, and both of these things are in equilibrium. Does the table really push up on the book? Yes, just as a spring pushes up on your hand when you compress it. Look at the figure, you can feel the spring pushing back on your hand. Similarly, a book lying on a table compresses the atoms in the table. Behaving like microscopic springs, the atoms in contact with the book push back on it. Since the book is in equilibrium, the net force on it must be 0. The table actually pushes up on the book with the same force that the book presses down. An ant trapped between the book and the table would feel itself being squashed from both sides, the top and the bottom. When you hang from a rope, the atoms in the rope are not compressed. Instead, the atoms are stretched apart. A tension force is established in the rope. A rope undergoes tension twangs if you pluck it. How much tension is in the rope when you hang from it? If you are in equilibrium, then the tension must equal your weight. The rope pulls up on you and the force of gravity pulls you down. Since the equal and opposite forces cancel each other, you hang motionless. Suppose you hang from a bar supported by 2 ropes, as in figure 4.12. Neglecting the weight of the bar, the tension in each rope is 1/2 of your weight. The total tension force acting upward is half of your weight plus half of your weight. Together that totals your entire weight. The total tension force acting upward balances your weight, which acts downward. When doing pull-ups using both arms, each arm supports half your weight. Have you ever tried pull-ups with just one arm? Why is it twice as difficult? Answer, because one arm has to support your entire weight instead of only half of it. A spring scale can also be used to measure tension. When we weigh a bag of apples by suspending it on a spring, the scale reading tells us the weight. Consider a 1 kilogram bag of 10 apples weighing 10 newtons. Question. When you step on a bathroom scale, the downward force supplied by your feet and the upward force supplied by the floor compress the calibrated spring inside the scale. The compression of the spring gives your weight. In effect, the scale measures the floor's support force. What will each scale read if you stand on two scales with your weight divided equally between them? What happens if you stand with more of your weight on one foot than the other? Well, the answer is that the two scales together have to support your entire weight. If one foot is on each of two scales equally, then each will be supporting half of your weight. If one foot is standing more strongly on one of the scales, it will support more than half your weight, but the two scales together still add together to your total weight. Let's look at the girl hanging on the bar. So the sum of the rope tensions must equal your weight. The rope tensions means the forces in this rope and the force in this rope. Those two forces together have to add together to equal her weight. For example, if she weighs 100 pounds, there has to be 50 pounds in this rope, 50 pounds in this rope. When suspended by a single vertical scale, as shown on the left in figure 4.13, the scale reads 10 newtons. Let's pause and take a look at that. Here's the figure on the left side. Okay, so we have a one spring scale right here. It's supporting a 10 newton weight, and the scale reading is 10 newtons. If instead we hang the 10 newton bag from a pair of vertical scales as shown on the right in figure 4.13, each scale reads 5 newtons. Let's look at that. Now we have two scales side by side. Together they're supporting the 10 newton weight, so each one must be providing 5 newtons of upward force. Each one reads 5 newtons. The two scales pull up with a combined force equaling the bag's weight, 10 newtons. Since the bag hangs at rest, the net force must be equal to 0. The key concept is this: if a 10 newton bag is in equilibrium, the resultant of the forces applied by the pair of springs must equal 10 newtons. In other words, together they must provide 10 newtons, so each one provides 5. If the spring scales are oriented vertically, this is easy. 5 plus 5 equals 10 newtons. Okay, let me just reiterate that for both of these situations, the net force is 0. Both of these weights are hanging in balance, so the downward 10 newtons of gravity have to be balanced by upward 10 newtons, so that the net force balances out to 0. Okay, thank you very much.